In this video, I'd like to talk a little bit more about generating polygons. And this is just a little bit of brainstorming about how you can go about generating polygons based on geometry and stuff that's like inside of a Unity scene. So the first thing let's talk about is what defines a polygon. So a polygon is something that looks like this, right? There are edges and points that make it up. And really the question is like, how are we going to store this information in code? Well, I would start by creating a brand new small class called Polygon. And in this Polygon, I would probably keep track of a list of points. So let's do that. Let's just have a list of, and it could be vector 2 or it could be vector 3. I'll just use vector 3 for simplicity's sake. And I'll just call it points. So here's my collection of points for this polygon, and that's it. That's really all a polygon needs to be right now. It's just a collection of points. Now, if I want to draw this polygon on screen, and I have a, later in my code, I have an onDrawGizmos function. Inside this function, I would essentially do like a for each polygon that I have, ... And then in here, I would essentially loop through for in I equals 0, well, I is less than, my polygon dot points dot length, right? Essentially just looping over each one of these points, right? ... And then in here, I would do like a gizmos dot draw a line between this point and the previous, and that might be about it. And that will essentially draw these lines, 1, 2, 3, 4, or however many points that I have inside my polygons, right? So this is sort of the very basics. The first things that I would do is to set up the representation of a polygon, and then making so that once I do have some polygons defined in my project, I'm drawing those things on screen so I can see them. Okay, cool. So the next thing let's talk about is how do we go about actually creating these polygons? Well, the first and easiest method would be to keep it really simple, right? This is really going to depend on what your level design looks like. The easiest way, let's imagine that your level is constructed by placing a series of blocks and platforms that look something kind of like this, right? Excuse my terrible perspective 3D drawing here, but imagine you're just like placing down blocks, and this is how you build your level. And so you have a whole bunch of these sort of cubes in 3D space, right? Well, what we want is we want polygons that represent the surfaces that a player could walk on in this level. So essentially, we want polygons that represent a space that would look like this, right? If my crazy perspective drawing makes sense, right? So from the top down, this thing would kind of look something like this, where we have a series of cubes, right? And we would want our polygons to represent a space that looks something like this eventually when we're done, right? And this could be broken up however. Remember that we want polygons that are convex, meaning that we don't want anything that has like an inward edge like this, right? This is not going to work well for us. We want convex polygons, which means that in this example where we have something like this, eventually, we want this thing to be broken up into multiple convex polygons. So this could be broken up, ideally, actually, just into 2, right? These are both convex polygons. As an optimization, one of the ways that we should think about this is just keeping it really simple, right? Either just triangles or squares, right? 3 points, 4 points, that's about it. So one way to think about this is if this is just a bunch of triangles that looks like this, those are also convex polygons. That's great, right? Our mission and goal right now is really just to generate polygons and not care about whether they're convex or concave, not care about the optimizations behind them or anything. We just want to generate these polygons. So to do that, one very simple method that I could use is, well, we have these blocks here, right? Why don't I just say, you know what? Based on these blocks, each of these prefabs that I'm putting down, these blocks, I'm going to use the center position, and I'm going to say that each one of these blocks creates its own polygon, each one. And the polygon is defined by the center position. Well, the polygons will be defined by these positions, right? This corner, this corner, this corner, this corner, right? So here's one polygon. And then when I place this second block, it creates this polygon that looks like this, right? And you could probably easily see, like, well, if we are just creating polygons just by these floor tiles that I'm placing down, then we could generate these squares. We could generate these polygons, 5 of them, that just look like this, right? This seems relatively straightforward enough, right? The next thing that we'd want to do, ideally, is we kind of want to like merge these things together. And that's where the Clipper library can come in handy. There's a couple other libraries to be able to do this, and you could also just write your own logic. And I'll talk more about that in a second. How else could we generate polygons off of some surfaces like this, right? If this is what our level looks like. Well, another way that we could do it is we could look at all of the surfaces that are in our game, all of the meshes, the 3D meshes, right? So these are all drawing meshes. We could look at all the 3D meshes, and we could look at the normals of them. And a lot of games do this kind of thing, right? You can imagine a game where you had like a terrain that, you know, from the side might look something like this, right? And you're wondering whether or not, you know, a person can stand at any one of these positions, right? And maybe they can't stand at this position because it's too steep, right? Well, one thing that you could do is you could explore and look at the mesh itself, look at all the different faces of the mesh, and look at the normals of those. So remember, the normals are going to be pointing in a direction like this, right? This may bring back memories of talking about normals from an art course or somewhere else. So if you were to look at all the meshes, and you look at all the faces, and look at the normals, you could compare the normals with sort of the global upward direction. And essentially say, is the normal of the surface that I'm looking at similar enough to the global upward direction? And if it is, then that surface, that mesh, should be a polygon that I can walk on. Right? So this is another method to do it, and this is actually how it happens a lot for terrain, right? Terrain is actually made up of a whole bunch of like really small triangles or really small quads that are sort of, you know, constructed and have their own like height information about them and stuff. And so what the system could do is it could go and look at the normals of each one of those faces in any given direction, right? Sort of look at each one of them, compare each one of these normals to the global upward direction, right? So here's our global up direction. Compare each one of these normals with the global up direction, sort of traverse through them all, to determine which ones are valid and which ones are close enough, right? So obviously a normal that's facing the exact same direction would probably be valid. A normal facing, you know, perpendicular or downward would not be a valid space to walk on. And then you can kind of determine like what is the maximum angle that you'd want your players to be able to walk on, your NPCs to be able to walk on with your navigation system, right? So based on whatever that angle is, in doing your comparison, you could essentially do something like all of these are valid, right? And then maybe these are valid up here, right? And so then you're sort of figuring out, okay, I know that these surfaces, these meshes, these triangles, these portions of my terrain are all valid areas to walk on because the surface normals match closely with the upward y direction of my game, right? Now, these are just two methods, right? One is a pretty simplistic method, and one is a far more advanced method over here. Either way works. And different games have different strategies for building out their navigation meshes, right? The challenge here for us is just Figure out a system that works best. How is it that you want to develop your navigation mesh system? Do you want to do something simple? Do you want to do something a little bit more complex? There go my diagrams. Excellent. So let's talk about the next thing. Once I actually construct or have a bunch of polygons, right, those polygons may look pretty messy. You can think of that very first example where I essentially said, you know what, let's keep this really simple and let's generate polygons with each one of the cubes, right? And so the next task is, ideally, you would want one polygon that looks like this, right? Ignoring the fact that it's not, ignoring the concavity of this thing, right? We know that this can't be used for navigation meshes, but the goal right now is to just figure out the shape, just figure out the polygons. We'll break it up later, right? So one thing that you might want to do is sort of merge all of these polygons together into one nice, big, clean shape. You can imagine that your pathfinding system will just be more efficient if you have one nice, big mesh, one nice, big polygon, as opposed to having a whole bunch of these small polygons, right? You could imagine sort of like a worst case scenario in a game like this, where you have like a huge, huge grid, right? And say you had something that was like 100 by 100 grid, right? And you end up with a whole bunch of polygons, that just look like a whole bunch of these individual squares, right? When in reality, this could just be represented by one giant polygon, right? I'll let you determine which of those navigation systems is going to be more efficient, right? So really we want to go through this process to ideally sort of smash together these polygons to make it a little bit cleaner. This is where the Clipper library can come into play. So clipperlib does two things primarily. One is it does what it's called clipping, right? It clips polygons, which means that it can merge or do some sort of binary logic about polygons. The second thing that it does is it can sort of like extrude or compress polygons as well, which might be something that you want to use in the future. So the first thing that the Clipper library does is exactly exactly what we're talking about. You can pass into the Clipper library, which is just a series of points, right? Clipper library uses something called a path. And a path is actually the same thing as a list of integers. I think they call them like integer points. In points or point integers or something along those lines. And these are actually just, they have an x and y. That's it. And they're integers instead of floats. So you might have to do some rounding or an adjustment there, right? And then they also have an object that's called paths, plural, which is a collection of polygons. And a collection of polygons is really just it's a list of these, right? So a list of lists, right? A list of lists of, of int points, right? So whenever you see these, the paths or paths, really it's just like, it's just a rename of a list or a list of points, right? Which is exactly the same thing that that we sort of defined here. So what I can do with the Clipper library is I can say, all right, Clipper library, I've got some points for you. Here's a polygon. Here's the first one, right? Polygon 1. Here's a polygon. Polygon 2. Here's a polygon. Polygon 3. Polygon 4. And Polygon 5. You pass this into the Clipper library, right? Clipper library has a couple functions. There's like an add paths function. You would add a bunch of paths. And the way that the Clipper library works is there's like source or target or something else along those lines. You essentially would add one of the polygons as like a source or target, and then you would add all of the other ones afterwards, basically saying then that you want to do like a combining operation, right? So you call this add path function, you add all your polygons to it, then eventually you call your Clipper or your execute function, I think is what it's actually called, in the Clipper library. And in that, you'd want to specify that you want to do a union of all the polygons. And this execute function will return you back this one polygon. It will return you a single path, right, representing the one space of this entire thing combined. So the Clipper library basically saves you from doing some of this slightly more intensive math of, detecting where these things overlap and how they overlap and where, right? Clipper library is pretty powerful in this regard. Now, while we're talking about the Clipper library, the other operation that it can do is sort of expanding and extruding your polygons. This is really commonly used for video games when you have walls. So you can imagine if there were walls on the edge of our room here, right? If our walls were colored in black, we actually wouldn't want our navigation system to be right up against the edge of our walls, right? Because remember, the navigation meshes represent anywhere that an object can stand. So if we have a player that's this wide, a player can't actually stand at the edge position, right? Them standing at an edge position would mean that they're halfway in the wall. What we really need is we need our polygons to actually be brought in slightly. We want a representation that looks something like this. These are actually, like, this is more of an actual valid navigation mesh for us, this one here, because our player now at this point can stand at the very corner of these things and not be inside the wall. Well, this is another operation that the Clipper library can provide for us. There's a function that you can call in the Clipper library where you pass it, surprisingly or unsurprisingly, you pass it a path or a polygon. You say that you want to expand or extrude this thing. You give it the distance that you want to expand or extrude by. You also specify how you want to handle corners. It can kind of, it can keep corners sharp. It can round corners. It can do a handful of different methods with corners as it's expanding or contracting. And then it will give you back this final polygon. So this is essentially the tactics that I would go about using for generating polygons as a first step in creating a navigation mesh system, especially using the Clipper library. It's really powerful. For now, I wouldn't worry about unoptimized polygons. Don't worry about convex, concave, or anything like that. Really, it's just, let's get the shapes. Let's get it going so that we have the representation of the shapes, and let's worry about any sort of cleanup or optimization phases that we have to do later.